Okay, on to advanced gas laws. So there's a bunch of problems thrown into this section here, and hopefully being at the end of the semester, everything comes together and it's straightforward for you. So first, we're going to look at partial pressure. So just like mixing two gases together. So we can imagine if we pop these balloons, they each are different, put them in a balloon or put them in a cylinder or something like that with it. For stoichiometry, then imagine we have a reaction occurring and producing this gas, and how does that affect like the balloon or pressure in a gas cylinder? And the last one is the fusion and diffusion, and really easy, straightforward relation, and brings together kinetic molecular theory. So in the first one, stoichiometry, then, so we have kind of two cases where if we do a reaction, we're in a bomb calorimeter, and then we're just going to read out the pressure on it. And the other scenarios is what if we have this reaction in a balloon? I'll show you that in a minute. All right. So if we have a reaction and we only have one gaseous product, then at STP, then what we can do is just do our basic stoichiometry and find out how many moles of C, and then use the simple 1 mole equals 22.4 and do a ratio or dimensional analysis and solve for that volume. Equally, we can just simply take that moles and plug it in, and given those values at STP, 1 atmosphere or in 0 degrees Celsius, and solve for that volume too. So kind of not that much more difficult. If a reaction occurs and we heat it up or we're not at STP, then we can't use this relationship. We have to go to PV equals nRT. So kind of, again, I don't think it's that big a deal for you. And so the last one is if we have a reaction occur, and what if we have more than one gaseous product and something like this? So what we can do, this is the idea of partial pressures, and we can look at what's that pressure due to C, doing the same thing we did above, and look at it for D. And maybe the question is independent, but often it'll be the total pressure, and we simply add up those partial pressures. All right. And so this is the idea. Then the other one, we had it in a sealed container. We measure pressure. If we have it into a balloon, now we can think about the volume changing and what's the volume of this that we need for it. And so equally, same kind of idea, solving for this, just setting pressure. And so really exact same process for it. So the idea of a partial pressure is that we can actually treat, like we saw in the last one, treat them separately and and then think about the total pressure. Or we can actually, because they're gases and the way they don't interact or whatever, we can actually then sum up those gases individually and get the total moles of gas and simply plug that into PV equals nRT. In some problems, it's easier to do this. Some problems, it's easier to do that. But really, that's the beauty of it. So if you look online, you look for other ways to solve problems. Um, then there's a big difference in the pathways. Most of them, there's not a big difference in the pathways. And so here is an example in a grab from Kim Libre, and you can check it out. If you want, pause the video and try and do it. But the big idea is similar to dilutions. And so it's again taking the relationship PV equals nRT, and now you can relate it through the R to state one and state two. And the states that don't change, again, give us a relationship. And in this case, it looks very similar to M1V1 equals M2V2. And that's what's really happening. As we change the volume, we're diluting it. And so we're diluting the pressure for it. Equally, we can think about like the total pressure and the partial pressures if we have different gases. And there's a calculation for doing this. Um, and here's an example from your book, and you can look at this in more detail. But you actually don't need this new relationship. We see the same thing happening again with that other form of the ideal gas law when we think about state one and state two. So in here, we set it equals state one, rearrange it in terms of R. We can set it up for P2. And now we can just, instead of doing like the Avogadro's law, where we look at pressure instead of volume, we can do this. And in this case, N2 is going to be, or one of them would be the total moles. And if we rearrange this, then we can get it into this form where we get the mole fraction. which is just the moles of A over the total number of moles of A. So you already know how to do this just from your kind of basic understanding of ideal gas law. The last one is called diffusion and diffusion. It depends on if we're looking at time or the rate of it going across a barrier, those kinds of things. Um, and the idea is that if we have a mixture of gases in there, because they're colliding so much, they're going to have the same temperature, and so therefore the same kinetic energy. But because they have different masses, that means their velocity is going to be different. And then that just means we have different number of collisions at this boundary. And so we can simply rearrange this and set up this to get that relationship. And so what ends up happening is if we look at rate of it, then it's inverse. And if, however, um, we look at the time it takes for it to deflate, then we're because time is on the bottom of rate, right? Rate is like velocity, distance over time. And so it's inverse relations. And so this becomes a linear relationship between time. And you'll see these two examples then in the website between them. So what's kind of cool is that then we can track that time. We can figure out like the predicted based on different gases and identify a gas produced from here by doing a control with one gas like hydrogen and then do a different gas and we can use that to identify. So it's kind of a cool little thing you can track. So here's some examples of doing that again from Kim Libre. A common thing then comes up, what's the ratio? Calculate the ratio of it. I don't have ratios. I have you actually solve it for it, but equally the same thing you solve for one, and it's similar to solving for the mole fraction on the other problems. And so here's one with the time with it. And so you can again go back to here. We can see you could pause this and do this in more detail and see what's the time for neon giving xenon. And again, the whole idea is that because xenon is more massive from it, it's slower. So we're going to have less collisions per time because they have to have the same kinetic energy. All right, that's it.